Hello, and welcome to Astronomy 100. In this segment, we're going to continue our topic on the seasons. In the previous segment, we talked about all of the observable facts that you could see related to the sun and how we see the sun during different times of the year. And what we're going to do in this segment is we're going to relate all of those observed facts, the observational facts about the sun, into the concept of the seasons. Now, before we get started, it's important to remember that the seasons are not caused by the changing distance between the Earth and the sun. If you remember from the last segment, in reality, we are actually closer to the sun in the wintertime in the northern hemisphere, and we're actually further away from the sun in the summertime in the northern hemisphere. So, if you recall from the last segment, the reason why we experience seasons has to do with how the Earth is tilted on its axis compared to how it orbits around the sun. So let me explain a little bit about this picture here. This line right here that goes through the middle, it says the plane of the ecliptic. And what that is actually representing is the Earth's orbit plane. Think of it as the Earth goes around the sun. This white line is where the Earth is always centered on. So as it continuously orbits around the sun, this is always the plane of the Earth's orbit, and it never leaves that. Now, this white line here is perpendicular to that orbital plane. And what you'll notice is that the north-south axis of the Earth, what we call the rotational axis, is actually tilted by 23.5 degrees. So as the Earth spins on its axis, it spins around and around, but it is not spinning perpendicular to its orbital plane. And it is really this 23.5 degree tilt that is the cause for why we experience the seasonal changes that we do. And we'll show you in this segment how all of that adds up to those seasonal changes. So let's expand this outward a little bit. You'll notice that by looking at the entire orbit of the Earth, and again, just before we go into this, keep in mind that the dates, or the names of each season, I should say, are Northern Hemisphere names. So when you look at the entire orbit of the Earth around the sun, one of the things that's important to notice is that we have this 23.5 degree tilt, where the rotational axis of the Earth tilted relative to the perpendicular of its orbital plane. Now, the 23.5 degree tilt is always the same. So even if the Earth moves over here, it is still 23.5 degree of a tilt. Over here, it is still tilted 23.5 degrees. Over here, it is still tilted 23.5 degrees. That's really important to know, that the tilt always stays the same. The second thing that's important to notice is that notice the tilt is oriented in the same direction at all times. So if this is the North Pole of the Earth, let's say it's tilted towards the right, over here, still tilted towards the right, over here, still tilted towards the right, and again over here. So the 23.5 degree tilt always is the same, and the orientation of the tilt is always the same. What I want you to notice is, as the Earth orbits around the sun, this 23.5 degree tilt is going to make it so that sometimes the North Pole of the Earth is tilted in the direction of the sun, but then when we come all the way over here, the North Pole of the Earth is now tilted away from the sun, relative to the sun. And so as the Earth orbits the sun, as we are continuously moving, the tilt of the Earth on its axis is going to change from being tilted away all the way to the point where it's tilted towards, and then all the way back to the point where it's tilted away. So when you combine the orbit of the Earth around the sun with this tilt of its rotational axis, that is going to cause the seasonal changes that we do. So at this point, let's dissect this a little bit and show you how this tilt is going to give us those observed facts that we listed in the previous segment about how we see the sun in the sky. So let's switch to a different picture on that one. To show that this is truly happening, what I want to start with is a video. And this video is actually rather interesting. It's one of my favorites. What it is showing you is a picture taken of the surface of the Earth by a weather satellite. And this weather satellite is always parked in an orbit that is continually looking over the surface of the Earth from this particular point of view. And so when we click the play button, what will happen is it's going to take a year's worth of pictures and run them all together to show you a movie. And what you'll notice as we run through the movie is notice the surface of the Earth. Look at the details. They're always going to be the same. This is actually part of Africa here. And you'll notice the weather pattern is going to change every single day. It's going to look like it's very chaotic, but notice that it's always the same part of the Earth. What I also want you to notice is this line right here. In a previous segment of this course, we called this the terminator. The terminator is the dividing line between daytime and nighttime. And what I want you to notice is how the illumination of the Earth during daytime is going to change throughout the year because of the tilt of the Earth on its axis. So let's click the play button and watch how this progresses. Notice the illuminated part of the Earth is changing because of the tilt of the Earth on its axis. And this is, again, the course of a year where it's going to show you this particular thing happening. So as the Earth orbits around the Sun, it will change from being tilted towards the Sun to being tilted away from the Sun. Even though the tilt is the same, it's because the Earth is changing its position relative to the Sun. And we can actually see the evidence of this in that video. So let's move on to the other parts of this. In this illustration, it is not to scale. What I mean by that is, quite obviously, I hope it's understood that the Earth and the Sun are not this close together. But the idea of this illustration is to show you how the light from the Sun strikes the surface of the Earth and how the light from the Sun will illuminate different parts of the surface of the Earth depending on the tilt. If the tilt of the Earth in the North Pole, in this case, tilted towards the Sun, you'll notice that the light from the Sun seems to favor the northern hemisphere. And when the tilt of the North Pole of the Earth is tilted away from the Sun, the light from the Sun seems to favor or concentrate on the southern hemisphere. So when we are experiencing our summertime, the southern hemisphere is experiencing their winter time. And when we experience our winter time, you'll notice the southern hemisphere is experiencing their summertime. The dates on the calendar don't change. On the date of June 22nd, or sometimes it's the 21st, the North Pole of the Earth is tilted in the direction of the Sun. This is the day of the summer solstice, the first official day of summer. And then 6 months later, when the Earth is on the other side of its orbit and this 23.5-degree tilt has the North Pole tilted away from the Sun, this occurs on or about December 22nd, and this is the winter solstice for us in the Northern Hemisphere. But remember, if you lived in the Southern Hemisphere, it's your first day of summer, even though the calendar says December 22nd. And if you live in the Southern Hemisphere, it's your first day of winter, even though the calendar says June 22nd. So it's a very different idea down there compared to what we're used to. You can imagine having Christmas, even though it's still late December. If you lived in the Southern Hemisphere, Christmas occurs during the summertime, whereas for us it's the wintertime. Now, the last little part of this is perhaps one of the most important part, and that has to do with how the sunlight strikes the surface of the Earth. And to show you what I mean, I'm going to introduce a basic idea here. In this illustration, we have a standard flashlight. I purposely have chosen this type of flashlight for one main reason. This type of flashlight has only one function. It's either on or it's off. We have no way to change the amount of light that comes from it. Sometimes flashlights have the ability to turn this part right here. You can make the beam bigger or smaller. But this flashlight, we don't have that luxury. Now what I want you to notice is when the flashlight is oriented the way that you see here, where the light is striking the surface straight on, you'll notice that all of the light coming from the flashlight illuminates this part of the surface. And we're going to introduce the idea of intensity. By definition, intensity is the amount of light that hits a certain area. And what I want you to notice is the light that hits the surface is covering an area this big. All of the light hits an area this big. And if the area is very, very small, the intensity is actually higher. Let me show you the comparison. If I angle the flashlight down like this, what you'll notice is that it's the same amount of light. There's no difference in the amount of light, but how it hits the surface is more spread out. And so this would be a lower intensity because it's the same amount of light spread out over a larger area. So when the flashlight is at an angle, the intensity on the surface is less. When the flashlight is straight overhead, the intensity on the surface is more. It's how much light hits a certain size of area. How does this relate to the seasons? Well, let's put all this together. This is a bit of a busy screen, but we'll kind of take the bits and pieces and we'll put it all together. This first one is showing you the summer solstice for the northern hemisphere. Notice that the north pole of the Earth is tilted in the direction of the sun. And we're going to choose various locations on the surface of the Earth. So this first location is the latitude that is the Arctic Circle. Then we have the Tropic of Cancer. Then we have, of course, the equator of the Earth that runs like that, the Tropic of Capricorn that runs south of the equator, and then the Antarctic Circle. Let's imagine that we have 3 people at 3 different locations. Now this first person here that you see right up here, this is roughly the location of being where San Diego or Southern California would be in the United States. And what I want you to notice is on this particular location in its orbit around the sun, the north pole of the Earth tilted towards the sun creates the summer solstice. And as the sunlight hits the surface of the Earth, notice that in San Diego, the red arrow is pointing to straight overhead for this person. The sun's not directly overhead, but it is very high in the sky, getting close to being directly overhead. And so if you were in San Diego, the sun is very high in the sky. The light from the sun hits the surface of the Earth at a very, very steep angle like this. And what we have is a higher intensity. This intense sunlight will actually cause the ground to warm up a lot easier than it would be if the angle of the sun were different. So the intensity of the sunlight causes the surface of the Earth to warm up very easily when the sun is very high in the sky. Notice that if you were at this location on Earth, which is the Tropic of Cancer, the sun is actually directly overhead for your location. And if you're at the equator of the Earth, the sun is not directly overhead, but again, it's very, very close to it. So in summer, from North America, Southern California, the sun is actually very close to being directly overhead, and the intensity of the sunlight is the greatest it can be for the whole year. If we switch to either equinox, it could be either the vernal or the autumnal equinox. Notice that the Earth is in this position now. Notice the tilt of the Earth is neither towards the sun nor away from the sun. And so if you are in San Diego, this is straight overhead, the sun is much lower in the sky, and it's at the equator of the Earth now that you have the sun directly overhead. If we switch to the winter solstice, again, this is for the northern hemisphere, we are now over in this position in our orbit around the sun. And what you'll notice is from San Diego's latitude, directly overhead is here, but the sun is very, very low in the sky. The sunlight comes in at a very, very shallow angle. And when the sun comes in at this very shallow angle, the same amount of light is spread out over a larger area. So its intensity is less. When the sun is lower in the sky, the intensity is much, much less. So let's put all of this together to summarize this entire concept. If we were to be outside experiencing what we see from the sun and all of the things that we measure that go with it, for instance, if you recall, during different times of the year, the length of the day is long or the length of the day could be short. During different times of the year, the sun takes different paths across the sky, sometimes a very short path, sometimes a very long path across the sky. And then if we combine that with the intensity of the sunlight, we get a summary. So let's summarize all this on the screen here. During the summertime, what we have is very long days. Remember, on the summer solstice, we have the longest day of the year, and we have very short nights. This means the Earth heats up for a long period of time during the daytime and only has a short period of time at night to cool off. Long heating during the day, short period of cooling at night. Add that to the fact that the sun is very high in the sky, the highest in the sky it'll be for the whole year. That makes the intensity of the sunlight very, very strong. So what we end up with is a long day of very intense sunlight and a short night to make that heat dissipate back into space. When you put those two things together, we end up getting hot temperatures. The flip side of this is, during the winter time, we end up with short days, of course long nights, and you add to that the fact that the sun is very low in the sky means its intensity is less. So you get a short day of low intensity light to not do a good job of heating the earth, a long night to give that energy back, and when you combine those two, you end up with colder temperatures. So as you can see, it's not related to the changing distance between the Earth and the Sun, but it has to do with the tilt of the Earth and how that tilt is oriented with respect to the Sun to create the hot summers and the cold winters. We're just about out of time. I hope you'll join me for the next segment.